Okay, let's unpack this a bit. What if we told you that calculus concept you're digging into right now?
Integration, specifically.
Yeah, integration. What if it isn't just, equations on a page,
Right.
but actually a tool, something that can measure, well, how much actual sunshine a field of wheat
It
gets?
really does bridge that gap, doesn't it,
Yeah.
between the abstract math and the physical world.
Mm-hmm.
So today, this deep dive, and it's tailored specifically for you based on the sources you sent and tying right into that differentiation integration chapter you're looking at. It's all about using integration to figure out the total light, the
Right.
total amount intercepted by, say, a crop canopy over a period of time.
And knowing that total light, that's not just for fun, is it? I mean, plants use light for photosynthesis.
Exactly. It's their energy.
So the total amount they manage to grab directly impacts, well, how they grow and ultimately the yield, right? How much food we get.
Precisely. So the mission today is really to see how this powerful mathematical idea helps us quantify something real world, something constantly changing.
Like sunlight hitting leaves. Because light isn't steady.
Not at all.
It fluctuates all day long, clouds move in, the sun's angle changes with the seasons. You've got this rate of light hitting the plants that's, well, it's always varying.
And that's where integration becomes just essential. I mean, if you just measure the light intensity at one single moment,
You'd get a snapshot.
yeah, just a snapshot. But crops, they need the accumulated energy over hours, days, maybe even whole growing seasons.
Ah, okay.
And integration lets us sum up that continuously changing rate of light interception over whatever specific period we need.
So it's like taking all those tiny instantaneous light levels from moment to moment and adding them all up
That's a great way to put it.
to get the grand total of light energy they received during that time. Like you're finding the area under the curve, if that curve is light intensity over time.
You've got it, finding the area under that curve. And what's really pretty fascinating for agriculture is linking that total light figure,
Yeah.
which, by the way, they often measure using special sensors out in the field.
Right.
Linking that figure directly to models that can then predict crop growth and potential yield.
Because the plant's total photosynthetic work is tied directly to the total light energy they captured.
Exactly. It's very closely tied.
It really shows how integration lets us move from just knowing a varying rate, like light intensity, to getting a really meaningful total quantity for something dynamic in nature.
It's a perfect example, I think.
Mm.
It shows how these mathematical tools you're learning are, well, fundamental to understanding and quantifying processes in biology, environmental science, agriculture.
Fields you might not immediately connect with calculus class.
You might not know.
So wrapping up a bit, we've seen how integration gives us this powerful way to sum up something that changes continuously, like light hitting that crop canopy. To get a really crucial total amount over time, it connects abstract math ideas to very practical, real-world things.
Absolutely. It shows
Yeah.
that connection clearly. So thinking about how integration totals things up over a duration, here's maybe something for you to ponder as you continue with your studies. Beyond just light on crops, what other natural processes out there vary over time? Think about maybe nutrient absorption by soil,
No, interesting.
or even how quickly a whole forest grows over decades. Could those be better understood, maybe measured, by integrating their rates of change? Something to think about.